Hey, what's up guys? I hope that you're ready to learn. In this lesson, I'm going to be giving an introduction to collisions to a year 11 physics standpoint. So before we start the lesson, a little bit about me. My name is Danuga Marnage and I'm a maths and science tutor from kindergarten through to year 11. So if you want to book some personalized coaching with me, whether that be a one-off session or a recurring session, and it can even be one-on-one sessions, or it could be group sessions, anything like that, my contact information will be in the description of this video, so hit me up if you want to discuss that. Now let's talk about collisions. So before we start drawing up diagrams and doing calculations, let's first explain what is a collision. So a collision is where two or more objects come into physical contact with each other, and in this process they redistribute their momentum and their kinetic energy. Some examples of collisions are going to be car crashes, bouncing balls, and explosions. And some types of collisions are going to be elastic, inelastic, and explosions, which are actually part of elastic collisions. And I'll explain why. Let's look at momentum. So, momentum is a very important quantity of motion that is very misunderstood because people rush to look at the formula and to do the maths, but they don't think about the intuitive definition of where momentum exists in the real world. So to make it very memorable, I'm going to put this into the real world aspect. So as you can see here, there's a sport called soccer. And what happens in the sport is there's this green goalkeeper here, and his job is to prevent this ball from going into the goal. So how he does this is by putting his hand or his body in the way to stop the ball or to change the ball's direction of motion. So let's watch a quick demonstration of a goalkeeper in action. So pay attention to some key details I'm going to be explaining in this situation.
Johnson places the ball on the spot, getting ready. That man literally has a cannon for legs. Here he goes, winding up for the shot, and oh! The cannon has fired and hit Sterling directly to the face. We clocked that at a stunning 116 kilometers per hour.
Okay, so as you can see here, the goalkeeper has gotten hit by the ball at 116 kilometers per hour. And this is a very, very fast pace, especially for a collision with a human. So something you may have realized is that the goalkeeper is still alive and well. And the reason is because of momentum. The soccer ball, even though it has a very high velocity, the momentum is what does the damage. And the momentum of the ball is quite low. Can you pause the video now and think of a reason why the soccer ball has less momentum than, for example, a cannonball? So now you've rewinded the video, you'll think about it and realize that the mass is what causes this. Otherwise, what else differentiates a cannonball and a soccer ball, of the same size? It's the mass, right? Because if I ask you the question now, imagine this same situation, but instead of a soccer ball, it was a cannonball. Imagine the man's face. It'll be something like, this maybe, where it's a lot more worse for wear because of the momentum of the cannonball. So let's now look at the formula for the momentum. The formula for the momentum, where momentum is P, is a mass times the velocity. And the units are kilograms and meters per second. So the unit for momentum is kilogram meters per second. And this is how we calculate the momentum. So in physics, when we learn a new unit and a new measurement, we have to always consider, is it a vector or a scalar? So if we look at the composition of momentum, which is mass and velocity, we find that mass is a scalar, but velocity is a vector. So overall momentum is a vector, meaning it has both a magnitude and a direction. And the law of the conservation of momentum is that in a closed system, the total momentum before and after the collision remains the same. And I'm going to explain this in more detail in just a minute. So now let's have a look at kinetic energy. So the intuitive definition for kinetic energy, this one's a bit more harder to put into a real life context, but it's basically the energy in the motion. And we can quantify this using the formula half mv squared. So again, we think, is kinetic energy a scalar or a vector? So m is a scalar, v is a vector, and the second v, because v squared, is also a vector. So what we come to find is a scalar times a vector is actually a scalar, because a vector times a vector becomes a scalar. And the reason is because of the dot product formula, which is something you can quickly Google. I'll explain it in a different video, but just for basic understanding, a vector times a vector becomes a scalar. So overall, kinetic energy is a scalar, meaning it hasn't got a direction. So, an object of the same size and velocity moving to the top versus moving to the bottom has a different momentum but the same kinetic energy, and that's an important distinction to understand. Let's now look at the conversion of these two in elastic collisions and inelastic collisions. So, in an elastic collision, the momentum is conserved. What this means is that the net momentum of all of the colliders equals the net momentum of all of the colliders both before and after the collision. The same thing applies for kinetic energy. The total kinetic energy for all of the objects before collision equals the kinetic energy for all of the objects after collision. Now, the same can't be said for an inelastic collision, where the momentum is conserved, but not the kinetic energy. The kinetic energy actually becomes into different forms, because you may think, how can we lose energy? We know about the principle of the conservation of energy, so obviously energy can't be lost. Well, the reason that energy actually happens to lose is because that kinetic energy becomes heat energy, sound energy, and is used to deform the objects. So think of a car crash. When there's two cars coming towards each other, you will hear a loud bang, you will see fire and heat and light, and obviously if you see in a car wreck, the shape of the wrecked car is very different to the shape of the intact car. So this is the reason that the kinetic energy is not conserved. And an explosion is actually the reverse of an inelastic collision. So basically, if you think of an explosion, think of a grenade. We have a grenade here, and what happens to the grenade is that the pieces of the grenade explode and fly apart. If we actually re-roll time and rewind time so it's flowing backwards, all these individual constituents form one grenade once again. So this is why we can still use the same formulas for an explosion, because it's pretty much an inelastic collision in reverse. So the same properties apply. So the momentum is conserved, but the kinetic energy, not so much. Let's now look at the differences between inelastic and elastic collisions in more detail. So in an elastic collision, we see that the momentum is conserved, so is the kinetic energy, and the number of objects has no change. What this means is that if there's X amount of objects coming into a collision, those same X objects leave the collision. An example is the game billiards, where you shoot the ball. It's called pool or snooker as well, where the two balls come into contact. So two balls collide and two balls come away, and it's the same two balls. So if you see a collision where the number of objects is the same before and the same after, and they're the same objects, then you can confidently say that this could be an elastic collision. Now this is a simplification, so just roll with it if you know a bit more detail. An inelastic collision, as we know, the momentum is conserved, not the kinetic energy, and the number of objects can change. So if you look at an example of an inelastic collision is where two cars collide. If I have car A and car B, and they're moving like this, they collide, and then they move off in a certain direction as one big clump of metal. As we can see, before there's two objects, and now there's one object. So this is characteristic of an inelastic collision. Another example, let's look at the reverse inelastic collision. If we look at a grenade, like at the beginning, it's just one grenade, right? It's just one piece. Then what happens is after the mechanical system inside the grenade explodes, all of the pieces fly apart. So first we had one object, now we have like 42,000 or however many pieces are in a grenade. It's probably less than 42,000, but this is what I mean. The number of objects actually changes in an elastic collision, in an inelastic collision and an explosion. Now that we fully understand the theory and the intuitive nature of these, we're now allowed to look at the equations. So I've supplied two basic equations, which are the conservation of momentum and the conservation of kinetic energy. So as you can see, this only works, or these particular formulas in their current form only work when there's two objects colliding. If there's more than that, then we just add one more object, so MA, MB, and MC, and then VA, VB, VC, VD. It can go on like that. I'm going to show you how to do that in the coming questions. So over here, we have a list of, what's happening. We have a list of what the pronumerals mean. We have a small diagram of pause the video now and tell me what type of collision is this. So rewind it or pause it, and now you unpause it, and now you will see it's an elastic collision. Obviously up here, elastic collision, because the objects, there's two objects before, two objects after, and they're separated. So in an inelastic collision, the only difference is this equation here does not apply. Just this equation applies. So now we have all the tools to answer these questions. So let's answer some questions. Alright, now we understand all the theory, let's jump into some questions. we have a 20-gram bullet moving horizontally at 50 meters per second, hitting a 7-kilogram block, which is at rest. The bullet then embeds in the block, and after the collision, we need to find the speed of the combined block and bullet. So before we continue with the question, we need to figure out, is this going to be an elastic collision or an inelastic collision? So pause the video right now and come up with your answer. If you have it worked out, or if you're still a bit stuck, let's work it out together. At the beginning of the motion, we have a bullet, and it's going towards a block. The bullet is 20 grams. It's moving at 50 meters per second. The block is 7 kilograms. And what happens after is the block gets the bullet lodged inside of it, and the entire thing moves. We need to figure out the velocity of the motion. Is it moving slowly or is it going fast as hell? So we need to figure it out. But anyway, as we see here, we start off with two objects and now we end up with one. So this has to be an inelastic collision. So let's take this. And by the way, always draw a diagram when you solve questions. It makes the question much more easier to digest. You're gonna make definitely like 50% less mistakes, because, and the biggest thing that the diagram helps with is direction, because sometimes direction in more hard questions, like the question up here, direction gets like, tricky. So drawing diagrams helps. So now let's jump into the question. So we know it's an inelastic collision, and if we think back to the lesson, what we know about the properties of an inelastic collision is that the momentum initially equals the momentum finally. If we think about the initial momentum, it's going to be the momentum of the bullet plus the momentum of the block, and that should equal the momentum of the combined mass. And we know that the momentum formula, P is equal to mv. Now, this is the most important thing in the entire video, what I'm about to say. So, and I guarantee you, at least 10 of your friends are going to make this mistake in the test. So I can't help them, but I can help you. So pay close attention. This very careful nuance is the velocity has to be meters per second, the mass has to be kilograms, and therefore the momentum is going to end up being kilogram meters per second. These are the units, and we cannot neglect the units. If we neglect the units by putting in the wrong units, we're going to get the wrong answer and get penalized severely. So always remember these units. Now let's begin to fill this out. So we know that the momentum is the mass times the velocity. So the mass of the block is 20 grams. Remember though, we want kilograms. So it's going to be 20 times 10 to the power of minus 3. I've done it like this so I can really emphasize to you guys that it's super important to convert into the correct unit of measurement. So this is 20, like the mass of the bullet, the velocity of the bullet, 50 meters per second. Then the momentum of the block is going to be 7 kilograms times 0 because it's at rest, right? And this goes to the combined mass momentum. So the combined mass is going to be 20 times 10 to the power of minus 3 plus, it's going to be 7. And the velocity of the combined mass is what we're trying to find. We put VF and we're solving for VF, okay? So now what we're going to do, we're going to rearrange this equation. VF is going to equal to 20 times 10 to the power of minus 3 times 50. This just cancels to 0, so forget about it. We bring this down to the bottom, and this is going to be 20 times 10 to the power of minus 3 plus 7. Now what we're going to do is use a calculator and, solve this. So it's going to be 20 times 10 to the power of minus 3 multiplied by 50 meters per second, and it's going to be 20 times 10 to the power of minus 3, again, plus 7 kilograms. Now our answer is 0.142. We'll just go to 3 decimal places because the question is, the answer's in 3 decimal places. I kind of checked before, but it was in the question, so you all checked. Anyway, the velocity is going to be 0.142. So let's go back. The velocity is 0.142. 0.12 what? What's the unit? Always remember to put the unit. The unit is 0.142 meters per second. Let's check the question, and we got it correct, guys. We have used our knowledge to solve a question. Yeah, good job. Alright, cool. So now we're gonna quickly move on to our second question. which is going to be this one here. So let's read it out. We see that we have an artillery shell at this velocity, 2 pieces. So we start off with 1 piece, and now we have 2 pieces. So it's going to be, obviously, it's going to be an inelastic collision, because we had 1 and now we have 2, so it's changed, therefore inelastic. After the explosion, there's a 10 kilogram. The initial one is 30, so there's no guessing really what the third one's going to be. It's going to be 20. And this is the velocity of the 10 kilogram one. The other one goes up. Find how much higher it rises. So let's do that. So initially we have an artillery shell, and it's 30 kg artillery shell, and it's going up, and it's going up at 250 meters per second. Really important though, the most important thing at the beginning, no matter what we do, we need to define a positive direction. I'm saying that up is going to be the positive direction. So anything moving down has negative velocity. So 120 meters per second moving down, to recuperate, 120 seconds moving down is going to be negative 120 meters per second in relative context, because that's a negative direction. Right, so now what we're going to do is we go after the collision. There's object A and object B. Object A is 10, so object B and object C, so object B and object C. Then object B is 10 kg, so then this is definitely 20 kg. This one here is moving up. This one's moving down at minus 20 meters per second. It's moving down at 120 or moving up at negative 120. So moving in the positive direction at negative 120. In an equation, so let's go back here, if we do an equation like this, everything must be in the same direction. That's a really important thing to note. Go back to the question at hand. So this is I put negative 120 just to emphasize to you guys not to forget to incorporate this. Now we're going to solve it. So this is going to be inelastic. So the initial momentum is equal to the final momentum. Initial of the artillery equals the momentum of the 2 constituents. So 30 times 250 is going to equal to 10 times, and part B was going up now, so V of B finally plus 20, and 20 is going down at, no, I had these flipped around, so this one is going at 20, and this one's going at 10, so the one going down is at 10, so the one we don't know is 20, the one we do know is 10, and this is going at minus 120 meters per second. Alright, now what we're going to do is we're going to solve this question. So we bring this to this side and then divide by this. We end up with the expression, the velocity of part B finally is going to equal to, we won't even need the finally because part B only exists after the collision. So the velocity of B is going to equal to 30 times 250 plus 10 times 120. Since this comes to this side, the minus becomes a plus, something we need to consider. And we put the whole thing on 250. No, we put the whole thing on what's in front of this, so 20 is going to be 20. And now let's just put this in our calculator and see what the solution is. So 30 times 120 plus 10 times 120 over this, and this is going to be 435. Alright, so we know that the final velocity of part B, so this one here going up, is going to be 435 meters per second. The question told us it's going up, and the solution we got is a positive number. This reinforces our assumption and gives us a sign that we could be correct. If we happen to get a negative number accidentally, if I accidentally had a negative in front of there and my solution was a negative number, what this would tell me is I made a mistake somewhere. And when I check my mistake, I go, oh yeah, I made a mistake here. Back to normal, alright? If we assume it's going in the positive direction and it ends up as negative, a mistake. But if we assume it's going in the positive direction and it happens to be positive, or we assume it to be going in the negative direction and it ends up negative, that's fine. So always have a brain when you do these questions. Don't just mindlessly write shit. Really think about it and be smart about it. Come on, you're doing a hard subject. Use your brain is the most important skill. So let's just jump into the question again. 435 meters per second. Now we need to find out how high it goes. Now I'm going to do 2 different methods and they're going to give me the same answer. So first method, I'm going to convert all of the potential energy, I'm going to convert all the kinetic energy it has into potential energy. This is a method called the conservation of mechanical energy, and this only works when a conservative force is acting on the object. So the only force acting on the object is gravity, because gravity is a conservative force, meaning that it conserves the mechanical energy at any position of height, what that tells us is that we can convert kinetic energy into potential energy. Let's do method 1. So it means the kinetic energy initially should equal the potential energy finally. Assuming at the beginning we consider to have full kinetic energy, and at the end we consider to have full potential energy. Immediately just cut that masses because it's going to be the same thing. We're just going to have, part like object B being here, and it's going to go up. Alright, so we cut that. We can, and we're solving for H, so we just bring the G to this side. So we have, V squared on 2G is equal to H. And yes. So now we're going to find H, and H is the height. So 435, because that's the velocity, and 2G is going to be 9.81. Okay, so let's solve this. So let's open up our calculator. So 435 squared, so it's going to be a large number, be braced for that. 2 times 9.81, and this is going to be our answer, 964. So looking back at the question, it was giving us to like something like 1 sig figures. I mean, the question obviously wants us to be more specific, so we're gonna write everything because the answers tell us. In a test where we haven't got the answer next to us, obviously we should round this to 1 sig fig because 10 kgs is 1 sig fig, but this question wasn't thinking about sig fig, so you don't have to. So yeah, therefore it's gonna be 9644.49 meters above. Now I'm going to solve method 2. So method 2 is using kinematics. So kinematics, what I like to do is list out all of my properties of kinematics, and I'm going to do the positive direction being up, as always. We're trying to find the displacement that we've gone up. The initial velocity is 435 meters per second. Final velocity is 0 meters per second. The acceleration is minus 9.81 meters per second squared. Now let's find S. So the equation we're going to use is, it's going to be V squared is equal to U squared plus 2AS. I'm pretty sure that's it from memory. We're solving for S, so always rearrange first, then substitute. V squared minus U squared on 2A is equal to S. S is going to equal to 435 squared minus 0 squared, so don't worry. It's V, by the way. Oh yeah, cool. So the V is going to be 0, so 0 squared minus 435 square, whole thing on 2 times 9.81. And as we can see, the numerator is going to be positive, sorry, negative. The denominator is going to be positive. So overall, no, hang on a sec. Oh yeah, here we go. This is negative, so we need to put negative here. So the denominator is going to be negative. So then overall, a negative divided by negative is going to give us a positive. The positive answer is going to be 0 squared minus 435 squared, whole thing on 2 times minus 9.81. Oh my god, it's the exact same answer. Here we go, guys. We're using our brain, and things are easy for us now. So this is, let's check it again. Maybe let's check if the calculator is like helping me out. Let's put 19 and see if it's different. Obviously it's different, so this is the answer. 9644.49. This is the answer, meters. And this corresponds here. Now, something that confused me, sorry guys. So, this is the answer from both methods, method 1 and method 2, they're the same. This looks good. Something that confused me was the question actually had a 4 here. But I used 2 entire methods and I got the 9. So if anyone can tell me why this was there, I'm assuming the question made a typo, but maybe I misunderstood the question, and that's why both methods yielded a different answer. So try the question yourself and see if you can get this, but I don't think you will. I think that the answer is the answer that I got. So, alright guys, we're going to do a final question now. So take a look at this question, pause it, analyze it, and see what you can understand from it. Pause it. Alright, cool. Now we're going to do the question. So what we see here is we have 2 balls. They hit, and instead of bouncing this way or going this way, they're going to go this direction. So it's a 2-directional. It's going to be a 2D collisions question. I'm going to show you how to solve 2D collision question. So what we need to do is first we look at the question and we see that the question is asking, is it elastic or is it inelastic? Since we don't actually know, we can't assume it's either of them. But what we do know is no matter what type of equation it is, it's going to be, the momentum will be conserved. So let's start there. We go there, and this is a pretty good place to start. Typically we say it's a good place to start, that the initial momentum is going to equal the final momentum. Now what we can say is the initial momentum of just the x component is going to equal the final momentum of the x component, and the initial momentum on the y component is going to equal the initial component of the final component of the y component. So now we're going to solve this. So in the x direction, I'm going to say this is the positive x direction and this is in the positive y direction, similar to a Cartesian plane, and these go on forever, so don't worry about the length of the line, it doesn't mean anything. So we're going to solve this. So we'll start before. So before we have m1, and m1 is going at 4.5 meters per second. So what this is going to tell us is that we have 5 kilograms, 4.5 meters per second. Now we need to do pfx. So we actually don't know the final speeds of the two objects, but we can just use v1 and v2. So it's going to be, so for m1's going to go down, so it's going to be 5 because the mass is constant, the velocity is v1, and how we actually separate this downward vector into just the horizontal component is we use trigonometry by building a right angle triangle like this. If the hypotenuse is this, the hypotenuse times this angle cos is going to be this. So then we can say that is going to be cos 30. And now the other one, the other ball is 2.5 kilograms, so 2.5 v2 cos 30 also, because we construct these 90-degree triangles where if we start here and we come down here, we're then multiplying by cos 30, and if we start here and go to this side, that's going by sine 30. So a really important thing to know. So hang on a sec, I need to grab something. Okay, never mind. So over here. Alright, cool. So now we're going to solve, this is just one equation, right? Just one equation. Now we're going to do in the y's. So on the y, the initial momentum of the y is 0, because this is the y direction and there's no y direction movement here, right? I'll recuperate. This is the y direction and initially there's no y direction here. So it's just straight going to be 0. And the final y direction is going to be, we have this, we need to find the vertical component, and this, find the vertical component. The vertical components are going to be, for this one, we'll do m1 first. So m1 is 5 and so v1 is going to be 5 v1 sine 30. But we need to see that this is actually going downwards, right? This is going downwards. So the vertical component of this is going to be downwards like this. Because it's downward, opposite to the positive y direction, we need to put a negative in the front. So let's go ahead and do that. Put a negative y here, plus, now let's look at b. b, m2 weighs 2.5 kilograms. So 2.5 kilograms. It's going to be moving at v2 sine 30. So now we have two equations. Let's simplify them before we do anything. So 5 times 4.5 is going to be 22.5. 22.5 is equal to, and then cos 30 is going to be root 3 on 2. So 5 root 3 on 2 v1 plus 2.5 times cos 30, that's just going to be 5 root 3 on 4, jeez, 3 on 4 v2. Now what I'm going to do, I'm going to multiply everything by 4 just to get like not real numbers, like easy numbers to work with. So 22 times 5 times it by 4 is 90, yes, sick, is equal to 5 root 3 v1 plus, no, it's going to be 10 because you must not do by 4, so it's going to be 10 here. This is going to be 5 root 3 v2. Now we divide everything by 5 because this makes it easier once again. So 90 divided by 5 is 18. This is 2 root 3 v1 and this is going to be root 3 v2. What's 18 divided by root 3? It can be 6 root 3. So let's get even simpler than that. Let's go 6 root 3 is equal to 2 v1 plus v2. This is a super simple relationship between v1 and v2. If we can get another relationship like this, it's wraps. The question is solved. So let's do that. So as you can see, we have this equation here. So let's bring this to this side so we can get rid of this minus plus here. So we bring this to this side, and sine 30 is half, by the way. So we have 5 on 2 v1 is going to equal to 2.5 times sine 30 is going to equal to 5, because this is 5 on 2 and this is half, so 5 on 4 makes sense. This is going to be v2. Now we can cut the 5 here and the 5 here. We can also turn this into a, we can multiply everything by 2. So this is cut and this becomes a 2. Then we can cross multiply 2 v1 is equal to v2. This is our second equation. So now we have 2 equations and we can use to solve for v1 and v2. So let's substitute equation 2 into equation 1. So we know that v2 is going to equal to 2v1. So 6 root 3 is equal to 2v1 plus v2, but v2 is equal to 2v1. So it's going, this is going over equal to 2v1. Then 6 root 3 is going to equal to 4v1. So v1 is going to equal to 6 root 3 divided by 4. So 3 root 3 on 2. Then therefore we have v1 is going to be this. Then v2 is going to be 2 times v1 times it's about 2. This is going to be 3 root 3. This is meters per second and meters per second. Super important that we make it meters per second, because in the question itself it gave it to us in meters per second. Otherwise we'd have to convert into meters per second, and that would be another question on its own. So luckily this is, so far it's correct. Now we have the two velocities. Now what we're going to do, oh yeah, cool. So the first part is find the final speeds of the two objects. So I have the question here, and these are the two, what's it called? These are the two answers. So if I convert this to a fraction, yep. So 3 root 3 is equal to 5.1962, and divide that 1 by 2, and you get 2.5981. So this so far is correct. But the final part of the question is, we need to say, is it elastic or inelastic? So now the final part of the question is to say elastic or inelastic. Let's first understand what elastic versus inelastic means. We know that the momentum is conserved, so it has to be a collision. If it's elastic, then the kinetic energy is also conserved, but if it's inelastic, then the kinetic energy is not conserved. So how do we determine if it's elastic or inelastic? What we do is we find the initial kinetic energy and then find the final kinetic energy, and if these two happen to be the same, then we're on the money. It's going to be kinetic. No, it's going to be elastic. But otherwise, if it's not, it's inelastic. So let's figure it out. So the kinetic energy initially is going to equal to half m1 v1 squared. The reason is v2 is not even moving, different color. m2 is not even moving, so how can it have any kinetic energy? Because kinetic means energy of motion, and it has zero movement. So let's just figure this out. So it's going to be half 1 onto 5, and then squared, by the way, gotta have the square, and it's 4.5 squared. So the initial kinetic energy is going to be, let's just use a screen calculator to help out you guys. 1 on 2, 5, 4.5 squared, 50.625. This is the initial kinetic energy. Now we're going to solve the final kinetic energy. So the kinetic energy final equals the kinetic energy final of m1 plus the kinetic energy final of m2. This is going to equal half 5 kilograms. The velocity of m1, as we solved here, is going to be 3 root 3 on 2. So 3 root 3 on 2. And by the way, this is going to equal to the answer here, which is 2.56. 2.5981. So it makes sense. But I want to have it in real form. Even though this is physics, always put your answer in decimal. So I've done a bad thing. I've tricked you guys, and I've maybe made one of you make a mistake. In physics, never put it in exact form, because in the real world, you're not going to look at this and be able to tell what it's roughly equal to, right? This is physics. We deal with the real world, so always put the number. That's my bad, guys, but I'm going to fix this now by writing in the numbers. Obviously, I should be doing it off the calculator, but I have the answers handy, and it's like I've checked it to be correct. If you doubt me, just check it and you'll see it's correct. And always make sure you doubt your teacher, because that's how you learn for yourself. You cross-check and you self-learn. Don't take anything I say for granted. Really analyze it, and those who do are going to end up having more success than those who don't. So my advice to you in any aspect, don't take anything blindly. Always try to see the underlying mechanism and figure out what's going on for yourself. Don't just get information from one person. And because like in like a real life situation, forget physics. If you're looking at like an office, don't look at your boss as like the big daddy and you listen to everything he says. Try and understand what's going on independently, because then you'll know when to like strike sort of and get opportunities for yourself. So some advice that I've learned in my life in general is you should like try and look at the situation independent of what like people say and have your own view. So applying this back to learning, if I tell you something, check it. If it's not true, put it in the comments. You know what I mean? I could make a mistake and I could tell it to you and you may take it and make a mistake. So don't do this, guys. Alright, but we know it's correct. So yeah. Now I need to find the final kinetic energy. This is squared, and this is gonna be half 2.5 3 root 3 on 2. And something we should check is when two objects collide, typically, so not always, but typically what's going to happen is that the smaller object is going to have a higher velocity and the bigger object is going to have a lower velocity, right? This only makes sense. If you think of a car colliding with the truck might move back 1 meter. If it may go forward and just like crush through the thing. So think about maybe like a marble versus a bowling ball. If you throw the marble hard enough, it'll make the bowling ball move back a tiny bit, but the marble will go flying, alright? So thing to consider is if you have a question where there's a small object and a large object, and the smaller object seems to be moving faster at the end, that's a good sign. And as you can see, the 5 kilogram is moving at the this speed, with 2.5 kilogram moving at twice that speed because it's missing the divide by 2. This is a good sign. And for it to be elastic, right, the question is going to say it's elastic. So for it to be elastic, this right here has to equal 50.625. So moments of truth, let's check it out. So we have 1 on 2, we have 5, we have 3, square root 3, whole thing root 2 plus 1, 2, 2.5, 3 square root. Swear if this is wrong, bro. I've wasted so much time doing all these retakes. Can't be wrong. And yes, this is correct. This is 50.625. Alright, 50.625. So let's go back to the iPad. Joules, always. I'm gonna write this nearly. 50.625 joules. 50.65 joules. These are the same, which means the kinetic energy initially equals the kinetic energy finally, and therefore we can say that this collision is an elastic collision.